Given a system of multiple populations and having found a fixed point in this system, we may want to look at the stability of the fixed point. Sometimes though, it is not practical to find all of the eigenvalues of the Jacobian. We can use a set of conditions called the jury conditions. There are three conditions, and they are: the first one, b is less than 1. The second one is 1 plus b plus a is greater than 0. And the third one is 1 plus b minus a is greater than 0, where a is the negative trace of the Jacobian and b is the determinant of the Jacobian. In order to see where these conditions come from, we can use the fact that eigenvalues as a rule satisfy the equation of lambda squared minus lambda times trace a plus the determinant of a is equal to 0, where lambda is the eigenvalue. So this allows us to see the quadratic equation of p of lambda is equal to lambda squared plus a lambda plus b, using the definitions for a and b as previously. This is equal to 0. Now, attempting to solve this using the quadratic formula leads us to two cases for real and imaginary roots, i.e. when lambda 1, 2 is equal to minus a plus or minus the square root of a squared minus 4b all over 2, and when a squared minus 4b is less than 0, this gives us complex roots, and a squared minus 4b is greater than 0 gives us real roots, where the roots are the eigenvalues. We shall consider the case where the roots are complex first. Since b is equal to the products of the roots, and the roots are complex conjugates of each other, we find that b lambda 1 times lambda 2 is equal to each other, and which is equal to lambda 1 squared or lambda 2 squared. This is because they are complex numbers. Squaring an I will give you a minus, and it works out. So, if lambda I is less than 1, which is a condition for stability, this is only true if b is less than 1, because if b is less than 1, lambda 1 times lambda 2 is less than 1, and this is only possible when they are both less than 1. Now, we consider the equality a squared minus 4b is equal to the modulus of a minus 2 all squared minus 4 times 1 plus b minus the modulus of a, which can be expanded out to give you the fact that this equality holds. In the case of a squared minus 4b is less than 0, a modulus of a minus 2 squared minus 4 times 1 plus b minus the modulus of a must also be less than 0. And this can only occur with some rearrangement when 1 plus b minus the modulus of a is greater than 0. Now, with the properties of the modulus function, we are able to see that 1 plus b plus a is greater than 0 and 1 plus b minus a is greater than 0. So now we will consider the case where there are real roots, i.e. a squared minus 4b is greater than or equal to 0. So the largest magnitude of these roots is the maximum of lambda 1 and lambda 2 in modulus is equal to the modulus of a plus square root of a squared minus 4b all over 2. Now, we can note that r is an increasing function of modulus of a. So considering that if we say r is equal to 1, we end up with modulus of a plus square root of a squared minus 4b over 2 is equal to 1. This can be rearranged into modulus of a minus 2 is equal to the negative square root of a squared minus 4b, which can then be, by squaring everything, gives us modulus of a squared minus 4 modulus of a plus 4 is equal to modulus of a squared minus 4b. This can be rearranged to give modulus of a is equal to b plus 1. So r is between 0 and 1 only when modulus of a is between 0 and 1 also. So this gives us modulus of a plus b plus 1 is greater than 0, which we can then expand out to get the previous jury conditions as before. These are the proofs of the jury conditions when checking stability.